What is up, you guys? So welcome to another lecture on convex optimization applications. In this one, we're going to talk about a very interesting problem that is known as the shortest route, or also the shortest path problem. Okay, it's a very popular problem in graph theory and finds many applications, for example, in road networks. Shortest path algorithms are so important and they're applied to automate direction finding technologies between physical locations, such as, for example, if you're using your GPS for web mapping services and websites like MapQuest or even Google Maps. So people in Google have published a lot of papers on this topic and they've got their own solutions for these kind of stuff. Anyways, as I said, so the shortest route problem is applied to road networks as well. Other similar problems include the traveling salesman problem, which is a problem where you have to find the shortest path that goes through every vertex exactly one time. So you have one additional constraint. Unlike this problem, which is solvable, and there's many algorithms that are really well known that solve this type of problem, such as the Dijkstra's algorithm and the Bellman-Ford algorithm as well. The Viterbi algorithm could be included here. So Viterbi is very popular in decoding. So in the communication field, when you're sending, say, convolutional codes or these kind of stuff, you've got a certain trellis. And on this trellis, you've got a lot of options a lot of path to walk so as to find the optimal code, the optimal bit stream that you decode, right? Viterbi actually rules out many paths through forward-backward schemes. To be particular, you've got butterflies going to the back and these kind of stuff. So Viterbi is also well known in other topics. And all of those actually have an acceptable complexity. So this guy is probably quadratic in the number of vertices, so about 6 vertices. This has time complexity, I think, OV square, like that. On the other hand, Bellman-Ford has a time complexity of OV times E. That's the number of vertices multiplied by the number of edges. Okay. You've got Viterbi, on the other hand, has a time complexity of OTS square with some sort of adjustments, where S contains the sequence of states and T is the size of each state. Now this could grow depending on, this is adjustable. You can adjust the size of your Viterbi. There's a compromise here. Anyways, we're not going to take such an approach. No, we're going to formulate this problem as a linear program, LP. Okay. Now, as I said, the traveling salesman problem is really similar in a sense that traveling salesman seeks to find the shortest path, but there's an additional constraint that complicates stuff a lot. The shortest path, as we saw here, there's many algorithms that are optimal for this problem, and hence we can solve this in polynomial time. Now, due to this additional constraint where the traveling salesman should pass through every vertex exactly one time, traveling salesman is NP complete. So in other words, there's no algorithm that could efficiently solve it. And other problems that are also NP complete are problems such as finding the longest path in a graph. This is also NP complete. Other problems such as the Canadian traveling salesman problem and the widest path problem. So without further ado, let's get started on the shortest path problem. Now, as in previous lectures, I'm going to start off with an example and we'll try to, imagine the problem through a very small example. So imagine I've got 6 nodes, right? And at each arc of the graph or network, I've got a cost. The cost from going from 1 till 2 is 25. Say, going from 1 till 3, that's 20. And let's just fill in some random values. So at each connection, this could represent, let's say, distance. To go from 1 till 2, we've got 25 miles to cross. Going from 1 till 3, we've got 20 miles. And you can also see dual arrows. That is, going from 2 till 3 is the same as going from 3 till 2, right? So you could argue that this is a directed graph, right? So you can go forward, backwards between nodes. Well, one natural question is, well, why don't we have a directed arc from 1 till 2? Well, because node 1 is the source and we're trying to go from node 1 till node 6, destination. So there's no point of going from the source to a certain node then coming back, right? We don't need that. So that's why you don't see that. So in terms of a road network, we call this guy the source, 1 as the source, 6 as the destination, and all other nodes that are 2, 3, 4, 5 as transshipment nodes, because you could commute, you could go forward and backward, thus transship. So the problem here is to find the shortest route, right? For the sake of simplicity, and actually that's what this problem addresses, it's to find the shortest route to ship 1 unit. It's because finding the shortest route is irrelevant of the number of units you're shipping, right? So it's either you cross a certain path or you do not, and hence you're trying to see which routes you want to take. So the problem is, do I pass this path or not? And hence you're looking for, if we denote by xij as the number of units shipped from node I to node j. And again, the number of units is irrelevant here. So xij should be thought of as a Boolean, a binary value. It's either 0 or 1. But we're not going to model it that way due to the complexity of the problem. So we're going to leave it as a real number that is, bounded between 0 and 1. Okay? And we'll see what the solution will turn out to be. Okay, we'd like to model this as a linear program. So we don't want a mixed integer linear program or anything of that sort, because it will turn out to be too complex. So let's think about xij as the number of units shipped, but also keep to ourselves that the number of units is really irrelevant. Okay, let's pretend for a while that it is relevant, but then we'll see that it really isn't. Okay, so again, what is the problem over here? It's really to minimize the sum. If we denote the values on each arc or route as dij, that is the distance needed to go from node I to j, then we're really looking forward to minimize dij times xij, right, with respect to xij, right? This actually tells you how many units should be shipped and the distance covered, right? Now, one might get confused here. Well, what if I want to ship 2 units from I to j? Means that I'm going to cover dij twice, right? So in that case, it will be critical. But again, if you're shipping 2 units and passing, let's say, from 1 to 2, you're going to cover this twice. But again, when you stand at 2, you're going to look for the shortest route. So if you find the shortest route that is a subset of the optimal one, then logic suggests that you're going to push both units along this route. You're not going to, distribute units, because you're not minimizing cost here. It's not a network flow problem. This is a shortest route problem. Hence, you're going to push both units at this route. Now, in other types of problems, this is critical. For example, let's say you've got some congestion along some path, right? Let's say this metric is not distance. It reports some type of congestion or traffic along this route. Then, yes, you would want to balance. There's some load balancing going on. This is not the case here. And so if you have 2 units, you're going to throw both units at the same path. So it's as if you're minimizing twice the same cost. So the optimal solution will turn out to be the same, right? So what are the constraints over here? Let's see. So we're going to distinguish the source and destination constraints. So in the source constraint, think about it for a moment. Since you want to go from source to destination, then in our case, we're either going to take a decision to go from 1 to 2 or from 1 to 3, right? That being said, either one is going to turn out to be 1 and the other is definitely 0. So keeping that in mind, we can express this as follows: x12 that is going from 1 to 2 plus x13 that is going from 1 to 3 is 1. Right? That is, one of them is allowed to be 1. It's not going to be 0.5, 0.5. Well, again, for the moment, we don't know the solution. We're trying to figure it out. What if x12 and x13 turn out to be 0.5, right? But that's not going to be part of the feasible solution. It's due to the other constraints. So that is the source node constraint. Now, what about the destination? Likewise, the destination. Oh, and by the way, for the destination, you see those dual arrows? Well, you can drop this and this and this. Because what's the point if you're at the destination of going backwards? You're just going to increase the cost, right? So you might as well remove this double arrow. Okay. So at the destination node, we know that we're going to arrive at the destination through one of those three paths. So that said, if I'm pushing 1 unit, then one of those paths is going to be taken. So one of those paths is going to be set to 1 and the others are 0. That said, you can say that x26 plus x46 plus x56 is 1. This is referred to as the destination node constraint. Now we've got 4 more constraints, 1 per transshipment node, okay? And for that, we're going to follow the same logic here. So if I stand at any node, now if that node is part of the optimal route, means that the optimal route passes through this node. Let's say for the moment that node 4 is part of the optimal route, right? This could only mean that I am going to enter the node through some other node, and I am going to leave that node via some route leaving the node. So one of the path entering node 4 is going to be 1 and the others entering are going to be 0. And likewise, one of the routes leaving that node is going to be 1, whereas other routes leaving 4 are going to be 0, right? So that's the case where 4 is part of the solution. Now, if it is not part of the solution, that means that neither I am going to enter this node, nor am I going to leave it. That said, all the routes connected to this node and also all the routes leaving that node are all going to be set to 0, right? So whether this node is part of the optimal solution or it is not, this means that all transshipment nodes could be constrained as follows. The sum of units entering this node K is equal to the sum of units leaving that same node K. And those are referred to as transshipment node constraints. Okay. Set EK includes the indices of routes connected, entering, having a connection with node K, whereas LK is the set of nodes that node K could leave to, right? As an example, node 4, how could we enter node 4? We could enter node 4 via node 2 and node 5, whereas LK are all nodes that 4 could leave to. 4 could leave to 2 and 5 and 6. So here LK consists of 2, 5, and 6. Okay, so there you go. So let's solve this problem that we have over here on MATLAB. So I'll first start by defining this D vector over here. So as we did in the network flow lecture, we're going to stack all the entries of Dij in one vector and call it D. So D is going to contain all the costs of the network. So we're going to start by D11, D12, D13, 4, 5, and 6. And then D21 and D22 and so on. Now D11 is 0 is 1 doesn't go to itself. D12 is 25, so 25. D13 is 20. D14 is 0. D15 is 0, and D16 is 0. So 3 zeros. This is a really tall vector, but for organization's sake, I'm going to insert a comma and 3 points, which means that just put the elements of, let's say if I have 6 zeros over here, just put those. This is the equivalent of this. Okay, now let's go to node 2. So 2-1 is 25, 2-2 is 0, 2-3 is 3, 2-4 is 5, 2-5 is 0, and 2-6 is 14, right? Now you do the same thing for all other nodes, and you get this vector of size 6 times 6 of size 36. So if we run this, take a look at D, this is your D vector, okay? So this is my D, and for my A matrix, well, we didn't define the A matrix here, but if we do the same procedure as the previous lecture over here, A is going to contain number of rows as many as there is constraints. So in our particular case, we've got 1, 2 plus 4 transshipment nodes, that's 6. So we've got as many number of nodes as number of constraints. Let's start with the first constraint. Actually, we're going to write a function here, make stuff look better. We're going to create a function that gives me an index in a fact matrix given the indices over here. So if I give it 1, 2, it should be able to tell me where it sits in this matrix. Okay, we could have done this in the previous lecture, but I didn't think about that. I think it's very useful. So let's do that. This function takes in 1, 2, for example, for the variable 1, 2, and tells me where it should sit. Okay, how do I compute it? I pass it ij, and it simply returns the index in this matrix. Well, since I'm stacking 1, 1, then 1, 2, then 1, 3, down to 1, 6, then going back to 2, 1, 2, 2, and so on, it means that I am jumping depending on the row, so I minus 1, plus an offset in the jth index, right? And also let's do the inverse of this. This will turn out to be useful in the solution, because the solution is going to be a vector of size 36, right? So if I look at a 36 sized vector, it would be really hard to read. So I'm going to need the inverse function of what I just did here. Okay, so what I'd want is the route given the index. So this function would be called index to route. If I pass it the index, it should return in the first entry. So it's going to be ij. So I'm going to return 2 elements. I'll stack them in a vector, where the first one is the index divided by 6, and I'll take the seal of that, so I'll round it the highest integer, and the jth element would be nothing other than the residual, so int minus this guy right here, 6 times this guy right here, minus 1, right? Actually, since this is going to reflect the optimal solution, then n is going to be a vector. To cope with vectors, I'm going to return a vector to that vector. So this is going to be a column vector. So is this. Let's do this modification over here. Let's test those functions. So actually, I can't test them as such. Well, I could. How do I do that? Well, I just execute it over here. So root 2 index, if I pass it 1, 1 should be able to return 1, right? If I pass it 1, 2 should be able to return 2, 1, 3, 3, 1, 4, 4, 1, 5, 5, and 1, 6, 6. Then 2, 1 should return 7. If those outputs are consecutive, then what we did is correct for the moment. And there you go. So 1, 2, 3, 4, 5, 6, 7. Now let's do the inverse. Let's do index to route and pass it 1, then 2, then 3, 4, 5, 6, 7. The output of this should be 1, 1. The output of this should be 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, then 2, 1, right? So run this, and there you go. 1, 1, 1, 2, down to 1, 6, then 2, 1. You could have expressed this as such, as a vector, because we coped with vector arguments. Be careful, your vector should be a column, not a row. There you go. Okay? Now that we have those functions, let's make use of them. It will turn out to be really easy now to express the A matrix, where AX is B, and B contains, if I have this order, B should be 1, 1, and 4 zeros, right? So my B is 1, then 1, then 4 zeros. You could have done this as such, but it requires more writing, right? This is more useful for large vectors. So let's stick with this. Now, filling out A is very easy thanks to those functions. So now, as the first constraint, let's say the source constraint, I've got 1, 2, and 1, 3. All I have to do is say 1, 2 equal to 1, and 1, 3 equal to 1. This is the source. Right? Now for the destination constraint, is this guy over here, we've got indices 2, 6, 4, 6, and 5, 6, right? So in the second row, that is the second constraint, I should pass 2, 6, 4, 6, and 5, 6, right? 2, 6, 4, 6, and 5, 6. Now, let's go to the transshipment constraints. So keep in mind that sum of entering is equal to sum of leaving. So let's first do node 2, which is sitting at the third constraint. Now, to keep things clear, I'm going to exchange the position of this constraint. I'm going to just push it down to the sixth constraint. And why is that? So that things align with the node index. So the constraint number is equal to the node number, if you know what I mean. So I'll push that down to the sixth row, and do not forget to flip the entries here, right? Because once you do a permutation on the rows of A, you're doing same permutation on vector B. That said, now we're dealing with the second node. So over here, I specify 2. Okay, so what are the nodes entering node 2? So we've got 3, 4, and 1, right? So for that, I'll give them a coefficient of 1 because the others should, if we get it to this side, they should be given a coefficient of -1. Okay, so let's agree on one thing. You could, of course, bring this guy to the other side and say, oh, all the nodes leaving node K should be multiplied by a plus and those with a minus, but let's just get this guy over here and call it a day. So nodes entering are 1, 3, and 4. So 1, 3, and 4, right? And nodes leaving are 3, 4, and 6. So 2, 2, 2, and 3, 4, and 6, right? This is transshipment constraint for node 2. Copy paste this and do the same thing for node 3. You will get this. Then node 4, you get this. And last but not least, node 5. Okay, so now we have all the nodes. We have all the equality constraints for the nodes. Now we're ready to solve the problem. So over here, call xopt as the optimal solution and call linprog for this linear program. So for inequality constraints, I have none. For equality constraints, I'll pass a and b. For a lower bound, I'll just set it to LB for the moment and I'll define it. And upper bound, you could set it to 1. But trust me, you could also leave it empty. Pass an initial solution that we don't know. We'll leave it to the algorithm and some options. For options, we'll call optim options and specify that we're using linprog as a solver and we'll be using dual simplex. We will display our iterations as such and voila, let's run this. We have a problem. F is not defined. Oh, I'm sorry about that. D, that's D. Run. LB is not, ooh, my bad. So LB, since we're working with number of units, so give a positivity constraint on the variables as such, okay? The 6 square, run, other error. The number of columns in A equality must be, wait a second, what is A equality? What is the size of A equal? Oh, it's 30, not 36. Why? There's a problem. Oh, we forgot to define A over here. So A, oh man, we forgot to say that A is zeros with 6 constraints and 36 variables. So we initialize it as such. We fill out the ones. Actually, if you don't do this, let's see how MATLAB understands it. So that's your A, and it does automatically configure the elements that you did not fill out to be 0, which is good, but it tends to forget the other columns that you did not touch upon. Otherwise, it would fill in infinite columns, right? So to avoid this, you just mentioned that I want a zeros matrix that has 6 rows and 36 columns, right? So run, there you go. This is your optimal solution. And as you can see, it contains either 0 or 1, no matter what your upper bound is. So over here, we left the upper bound empty. You could have said, oh, I want an upper bound of, I don't know, 1s on my variables, right? So you could say here, upper bound, run, and you get a binary solution. Let's increase this furthermore. Say 1 million as an upper bound, run, and you get a binary solution, no matter what the upper bound is. Now, of course, you're not going to, do this. Of course, it's infeasible. So, yeah. Anyways, yeah. Okay, so for the moment, we've got this ugly looking solution, which if you come and look at it, it's hard to infer the optimal path. So that's why we wrote the second function. How do we use this function? Well, first, I'm going to read those indices that are 1. How do I do that? Well, first I find them, then I call the find function. Return the indices of those values in xopt that are 1. Okay, then to convert those indices to something useful, that is the by indices over here, ij, I'll call index to route. Tells me from I to j. So to do that, all you have to do is call index to route, pass it your indices that you found here. Now shorthand notation would be this, right? Get about this and remove a semicolon so that we could print it on the command window. There you go. this is your optimal path. So this reads as follows. You go from 1 till 3, then 3 till 2, then 2 till 4, then 4 till 6. Well, let's see which path it is. And this is your optimal path. Now let's see the total distance covered. So it's 20 plus 3, that's 23, plus 5, that's 28, plus 4, that's a 32 miles to go from source to destination. Node 1 till 6. Okay? Now you could have, I don't know why, yeah, it's over here. F val, that's the optimal value corresponding to this path. Okay, well, let's try to tweak the solution a bit. What if this guy was actually let's do a tie over here. So this is a 32, right? If this is a 14, then what is a 32 minus 14? Well, 32 minus 14, it's an 18. So at the limit, this guy, if it was an 18, then we have two solutions. 1, 2, 2, 6. Actually, that's not so accurate, because what if this path was better? Let's count this. 18 plus 5, that's a 23, plus 4, that's a 27. So actually we have a winner. 1, 2, 4, 6 would be our new solution. Let's try this. So 1, 2, 4, 6. Instead of a 25, I'll put an 18. Okay, here's my 25, 18. This guy is an 18. Run. There you go. 1, 2, 4, 6. 1, 2, 4, and 6. There you go. Okay. Now, what if this guy was a 1? Let's find out. We still have the same optimal path. No, 18 plus 5 plus 4. That's a 27. Now, what if this guy is a 1? Guy over here. What is the optimal path? Well, I think it's 1, 2, 6, because 18 plus 1 is 19. I don't think there's another path that adds up to something less than 19. Let's change this 14 to 1. 1 and 1. Run. 1, 2, 6. 1, 2, 6. There you go. A total cost of 19 miles, as you can see over here. Okay, so that's it for this lecture. I hope you understood what is the intuition behind the shortest route problem, how to think of it, and what the linear programming solution would turn out in this particular problem. That is, no matter what, no matter how you formulate the problem, no matter how you tweak around with those values, the solution will always turn out to be binary. It's a very important finding. Thanks for watching. If you found this lecture beneficial, please leave a thumbs up. Also consider subscribing to this channel to keep it going. And if you have any optimization problem that you would like to see me demonstrate or talk about, just leave a comment down in the comment section below. Also, if you have questions, I'll be happy to answer. Thank you for watching, and I'll see you in future lectures.